It is 6:39 a.m. on a cold September 12th morning, the year 1959. 2 years previously, the USSR had made history by successfully launching the first man-made satellite, Sputnik 1, into orbit around the Earth. On the pad of the famous Baikonur Cosmodrome, a flurry of human activity settles. Perched atop 280 tons of metal and fuel, a 344-pound device stirs to life. History was to be made once again. And with that, man reached out to touch another world for the first time. 2 days later, Luna 2 made contact with the surface of the moon, changing humanity's role in the universe forever. The Lunik program, or Luna program, was a diverse series of spacecraft designed for going to our moon and ranging from 1959 all the way until 1976. For this reason, I will be mainly focusing on the crafts of Luna 1 through 3 in this video. However, I do plan on making videos covering all of the Luna variants. With Sputnik's success and the space race ramping up, the race for records and milestones had also begun. By this time, both the United States and the USSR had been successfully launching satellites, but the failure rate for either side was still extremely high. Rockets and the spacecraft themselves were still in their infancy and were unreliable, glitchy, and most importantly, costly, taking up rare materials and resources, not to mention time, to make. Despite this, the race for space itself was over. We made it. However, a looming question remained. What was the next milestone? What is the next step? Collectively, the superpowers' answers were clear. They shall race for the moon. With the challenge set, a huge problem remained. To break free from Earth's gravity will require a massive amount of energy, and the voyage to the moon will be days long, with temperature fluctuations in the hundreds of degrees. This thing will have to be light, it will have to work, and it will have to last. With this in mind, the Russians went to work and the Luna program was born. Doubling down on reliability and casting off any unnecessary complexity, the design must be bulletproof, so they will use what already works, a ballistic missile and the chassis of Sputnik itself. Far from being forgotten, the R-7 series of rockets has a long and distinguished career of launching various devices and craft into space. Being the world's first intercontinental ballistic missile, or ICBM, it was originally designed to carry nuclear warheads, and was designed by the OKB-1 Design Bureau in Russia, being headed by one of the fathers of modern rocketry, Sergei Korolev. With the fact it even existed not being known to the rest of the world until its first launch, it was leaps beyond what the powers of the West could muster, using complex stainless alloys that wouldn't be known about until years later. It would arguably become the main contributing factor in the so-called Sputnik crisis, where there was a widespread panic of US public fears that they were losing the technical arms race with the Soviet Union, shortly after Sputnik's launch. And while the satellite was nothing new to most, the fact the Russians could put it up there without failure was. It would make use of 4 jettisonable booster pods, each containing both a fuel tank and an engine, as well as an engine in the middle affixed to its core stage. This middle engine would provide propulsion through the later half of the launch, not needing as much energy as the atmosphere thinned. The Semyorka, or number 7, is the original variant of the R-7. It was completely liquid-fueled and would be slightly modified to fit the flight paths and nose cones of the early Luna and Sputnik missions. Each of its RD-107 engines was 4-chambered, having only one engine per booster pod, and while looking at first glance like the rocket has many engines, the R-7's first stage only has 5, with even the small course-correcting vernier nozzles being fed and mounted to the main engine itself. Now, I won't go too much deeper into the R-7 here, because there's been a lot of media made about this rocket, but if you want to know more about the specs and details about the R-7, I do highly recommend you watch Scott Manley's video on the subject, since he gives a much broader and in-depth look at the R-7 and its other variants throughout the years. With each of its RD-107 and its single vacuum-rated RD-108 engines making around 200,000 pounds of thrust, the Semyorka was truly the first heavy-lift rocket, generating over 1 million pounds of thrust at maximum power. Still being used to this day, the R-7 is an amazing design and a huge accomplishment for a group working with 1950s technology, seeing steady improvements and upgrades over its lifetime. Designed and constructed by none other than the same OKB-1 Design Bureau who designed the R-7, the design and shape of the very early Luna craft were extremely similar to Sputnik 1, being a bit larger but still retaining the same layout. Just like Sputnik, the sphere itself consisted of 2 aluminum alloy halves, sealed together by means of bolts and O-rings. This simple yet effective method ensured that Luna would be just as robust as Sputnik had proved to be. What set Luna apart was the addition of more instruments, especially with Luna 3, and mainly the addition of a liquid rocket upper stage named Block E, which gave Luna the much needed boost to free it from Earth's gravity. Luckily, Luna 1 and 2 both took a direct approach to the Moon and did not orbit Earth. This negated the need to start the engine from orbit, where the environment of space could easily seize or damage the engine. I could not find numbers on how powerful this stage was, but given that the whole structure with Luna together weighed 800 to 1,000 pounds, it's safe to say that it wasn't much by today's standards. However, we do know it was automatically guided, to make sure the correct trajectory was obtained. Both Luna 1 and 2 weighed 344 pounds, and were exactly the same, making them one of the first spacecraft to make use of a common spacecraft frame, or bus as it's known, allowing them to be somewhat mass-produced, as opposed to the one-off creations like the aforementioned Sputnik program. Luna 3, on the other hand, would be quite a bit larger, at 614 pounds, but would also make use of the same spacecraft bus as the previous Luna craft, and would be extended and heavily modified to be a thick boy, having a different mission goal than the first 2 Luna craft. This was mainly a product of the failure rates common in the rockets and upper stages of the time, requiring multiple launches for a success. They were both designed as impactors, hurling themselves directly at the lunar surface and impacting it, as the name suggests. Luna 3 would also be one of the first spacecraft to make use of the 1954 invention of solar panels, and the first to use the solar array style that would become a staple of communication satellites in the future. It would also be the first spacecraft to ever use a camera system to take photos of the moon. These images would be of the far, or dark side of the moon, and would be transmitted back to Earth by October 18, 1959, a little over a month after Luna 2 made its impact. The camera of Luna 3 itself is a pretty crazy piece of early spacecraft tech, and with the only info on these things so rare to find, I'm honestly not even completely sure how some sections of it work. But I have a general idea, and I'll do my best when we get into it later towards the end of the video. All 3 Luna craft would be completely sealed from the outside environment and pressurized with nitrogen gas, even having a form of pressure switch to allow indication back on Earth of a hull breach, should it occur. This gas was also pressurized to about only 20% of the normal air pressure here on Earth. This helped minimize the stress from the vacuum of space, while still allowing airflow to move heat. As far as cooling is concerned, just like Daddy Sputnik, all of the early Lunas used a small central fan with a heatsink type system, which was combined with a dual-acting temperature switch for thermal control. The spacecraft body was externally wrapped in a thin layer of polished thermal shielding, which regulated the temperature being subjected to the craft from the sun and space itself. This was enough protection to allow the cooling system to primarily deal with the heat that was needed to be extracted by the internal electronics and power systems. In addition, Luna 3, with its more power-hungry and hotter-running instruments, would later incorporate a system of moving thermal louvers around its base that would open to expose the heatsink system, allowing it to cool rapidly on demand when needed. Overall, the early Luna craft were well designed and built amazingly sturdy, being able to shrug off micrometeorite hits while still taking accurate measurements for days on end. Its basic systems and robust instruments were the keys to its success, and we will talk about all of them, including that weird soccer ball thing, coming up. Now, as per Retro Rocket's tradition, let's see what makes this incredible machine tick. Lunas 1 and 2 were both powered by mercury zinc oxide batteries. These batteries are very stable, with mercury zinc still being used today in the form of button cell batteries used in hearing aids. The reason for using mercury was most likely twofold. Mercury, although harmful when absorbed by humans, has immense energy density, allowing it for a long runtime with stable voltage in a small package. The second was most likely an industrial factor. While Russia had much in the way of silver resources, these areas were rural, and the process to refine it was slow, and with much of the USSR still recovering from World War II, it's my guess that they saved it for where it was more needed, such as with electronic circuitry. I could not find confirmed voltages, amp-hour capacities, or power load numbers for Lunas 1 and 2, but given what we know about Russian spacecraft and the equipment they carried, they probably used around 100 to 150 watts, with them and Luna 3 all running between 26 and 28 volts DC. And while although Luna 3 would use some silver, that was necessary for its goal, and other battery technologies of the time would have not sufficed. Speaking of Luna 3, just like the craft itself, its power system was made for a different mission in mind. The mission to the dark side of the moon would see it having to operate for over 2 weeks, compared to the previous Luna's 2 days. For this, Luna 3 would need a much longer lasting power source. This came in the form of a solar panel and rechargeable battery layout. Most people today will be familiar with this type of system, and while not having modern storage technology like lithium-ion or higher efficiency solar panels, the process was nevertheless the same. The batteries in Luna 3 were rechargeable silver-zinc batteries. These were well known, being invented at the end of the 1800s, but were still highly expensive to make for the time. These batteries allowed the ability to recharge, while still being the best storage solution for the rigors of space. Silver zinc is also still used today, and can be found in digital watches, computer motherboards, and even torpedoes. These batteries would have a capacity of 6 amp hours, or around the size of a large cordless drill battery today. These were needed to power the camera, stabilization, and various measuring devices of Luna 3 when it encountered the moon, drawing way too much power than its solar panels alone could provide. Unfortunately, I could not find much about the solar panels on Luna 3 as much as I wanted to, but what I can say is most of these early panels have efficiency of about half of what our modern commercial panels do, being around the 10% mark. Since only one section of the spacecraft would be facing the sun at any given time, Luna 3 needed a whole big old bunch of these things to stay running, and keep its batteries topped off. It's not known how much these panels made, but the rule of thumb is that these early panels made about 1 watt per square inch. If I had to take a ballpark guess, I'd say that Luna probably made less than 100 watts with its solar panels, only needing to keep its low-energy radios and navigation equipment online for most of its journey. Starting with Luna 1 and 2, they each had 6 scientific instruments on board, with the Block E rocket stage housing its own radiation detector, and just enough space for its own special experiment. Somewhere on the Block E body was placed a 2.2 pound container of atomized sodium, which was then used to test a gas dispersion experiment in space. This experiment would go on to create an artificial comet for a brief time, shining brighter than most stars, and would be spotted through various telescopes around the world. The first instrument of the very early Luna craft we will talk about is the micrometeorite detector. This simple and rudimentary device consisted of an electrically charged metal faceplate that was pushed up and in place very lightly by metal springs. Whenever a micrometeorite would strike the plate, it would be depressed down from the impact, triggering one of various connections around its ring to become open. In turn, this open electrical connection was detected, and a signal was sent via telemetry data back to Earth, where it would then be counted. The next 2 of these instruments we will talk about went hand in hand, being used as a redundancy of sorts from what I can tell. They would consist of a Geiger counter and a scintillation counter. Just as in popular media, a Geiger counter measures ionizing radiation such as X-rays and gamma rays, with the addition to alpha and beta particles. I won't go too deep into Geiger counters, but for the context of Luna, I will say that while being relatively energy efficient, they cannot accurately measure high levels of radiation, nor can they distinguish one particle from another. Luna 2's counters would also go on to measure the electron spectrum of the Van Allen radiation belt, another first for the spacecraft. The other device in this pairing is a scintillation counter. This device did the same job as the Geiger counter, which is measuring ionized radiation, but used a completely different process entirely. This involved the outside radiation of space hitting a material that would glow, or scintillate, when struck with said radiation. The light produced from this glow would then be seen by a photodetector, turning it into the varying levels of current the craft would use for radio signals back to Earth. This analog way of capturing data will become a theme with Luna. As like with many spacecraft of the day, much of its systems and equipment relied purely on differing electrical signals converted to radio waves to send its data, streaming it in real time to be plotted and graphed back home. Next up on the list are Luna's ion traps. Like the name suggests, these instruments trap and gather ions and ionic molecules to be detected. They would capture and trap ions from space using both an electric and a magnetic field. All the Lunas would be given these ion traps. Luna 1 and 2 would have 4 around its capsule, with Luna 3 ditching 2 of them in place of other mission-critical equipment. And just as with the other instruments, it would also output a varied electrical signal to the main radio controller. The fifth device on Luna 1 and 2 was a fluxgate magnetometer. This was used to measure the magnetic field around the craft. This measuring tool would be comprised of 3 major parts: an exciting wire, a sensing wire, and the core. This would function by using the exciting wire to saturate or fully magnetize the core. This wire would then magnetize the core in pulses, raising and lowering the strength of the magnetic field. These pulses are then read by the means of electromagnetic induction through the sensing wire, which can be seen wrapped around the outside of the core. The outside magnetic field around the craft imparts added electrical noise to this process, making a calibrated tool able to read these variations, and thusly able to send back the strength of these fields, later to be mapped as Luna traversed through the Earth's magnetosphere. The final instrument on early Luna was the Cherenkov counter. This device was very similar to the scintillation counter in that it measures particle radiation, but used a third process to create measurements. This involved using a principle of physics. That being that whenever a particle is slowed by the material it is going through, it will produce light. This device uses such a material, and uses that light by means of, that's right, you guessed it, another photodetector, to convert and relay a signal back home. Luna 3 would be quite a bit different, on the other hand, only retaining the ion traps and the micrometeorite detector of the previous Luna craft. The main difference in Luna 3 was the replacement of these instruments with its complex camera system, as well as the addition of a mass spectrometer. This mass spectrometer, in layman's terms, measures the mass-to-particle charge in whatever is being aimed at, being able to gather readings on what material it comprised. Luna 3 would get within 3,900 miles of the Moon, and use this device to confirm the Moon's oxygen and silicon-based nature. The camera system on Luna 3 we will save for the special features section, as it has truly earned a spot in this video. If you would like to skip ahead and learn more about Luna 3's imaging system, I have put chapter timestamps in the video and feel free to discover that and the weird soccer ball. Both Lunas 1 and 2 would see them having no propulsion whatsoever, with Block E aiming and boosting them straight towards the Moon. This was also done via radio, as the Soviet designers were distrusting of the then unreliable automated systems. This would come to be a double-edged sword for the OKB-1 Design Bureau, as a slight millisecond delay in the firing signal would lead to Luna 1 missing the Moon by over 3,000 miles. Like most craft at the time, all 3 Lunas would be spin-stabilized, meaning they spun around as to not tumble through space, having no air resistance to use for stabilization. This spin would be imparted on Luna by Block E shortly after separation from its R7 rocket taxi. However, Luna 3 had a problem. It could not be spinning while taking photos of the Moon. For this, Luna 3 would need to be axis stabilized, or in essence, need to stabilize itself. For the 40 solid minutes needed to take its pictures, Luna 3 would use a combination of gyroscopes, light sensors, and a microjet-based thruster system. This thruster system used a highly pressurized tank of presumably nitrogen gas with 8 nozzles to center the spacecraft on the Moon. For the first 10 minutes prior to photography capture, these nozzles would slowly de-spin the spacecraft, being spin stabilized up until this point. After its goal was achieved, Luna 3's thrusters would then re-spin the craft, spin stabilizing it once again for the journey back to Earth and the completion of its mission. Navigation for Lunas 1 and 2 will be short and brief. They had none. While not having any sensors or means of navigation themselves, the Block E stage of all Luna craft did navigate through the radio commands mentioned previously before. It should be of note that the navigation and mission trajectory of Luna 3 was especially complicated. To stay within the radio stations of the northern-based USSR when coming back to Earth, Luna 3 would have to use a lunar gravity assist maneuver. At this time, this would be the most complex spacecraft maneuver ever undertaken, and the immense math and triple checking required was a logistical nightmare. To aid with this issue, the Soviets would employ one of the most advanced technologies they had at their disposal, the Strela 1 supercomputer. Being the Soviets' first modern computer, it was first manufactured in 1953. It would use a whopping 150,000 watts of electricity, and take up roughly 3,200 square feet. Its 6,200 vacuum tubes and revolutionary magnetic tape storage would crunch and confirm the numbers for Luna 3's precious gravity assist. As we have mentioned before, Luna 3 had gyroscopes and light sensors to help it track and image the moon. These sensors are what fed data to the thruster system, making Luna 3 able to stay steadily in place to take its pictures in space. I'm going to be grouping these devices into the navigation section of the video, since I feel that they don't quite fit into propulsion, even if they don't smartly navigate like modern craft do. The first of these is the gyroscope. Luna 3 would have 3 of these inside its shell, one for each axis, X, Y, and Z. These devices would use a spinning wheel trapped in a free-moving housing to measure motion. Once spun up, the wheel will stay in place using the principle of angular momentum, making any movement of the craft relative to this wheel observable, and thusly detectable. The second navigation tool Luna would need for its mission around the dark side of the moon is, ironically, a sun sensor. While being described as the dark side of the moon, these areas do in fact get lit up by the sun. To note, this event also takes place on the first and the last days of the moon's orbit around the Earth. As talked about in our Ranger program video, a sun sensor uses a lens or cover to project the light of an object, or the sun in our case, onto the center of a square series of 4 photodetectors. These photodetectors are used to initially sense the sun's presence, and then after this is determined, use the difference in the light between the 4 panels to sense any deviation. Whenever the spacecraft would start to veer off course, one of these panels would in turn start to dim from the moving center of light. This difference would then be detected and then used to help Luna stay on target. The final device in Luna 3's orientation system was the lunar sensor. This used the same basis as the sun sensor, but was much more finely tuned. It would see its photodetector placement being much more spaced out, as to detect the relatively close-up edges of the moon. All of these navigation sensors combined to make Luna 3 very stable, and allowed it the unheard-of precision that was needed to track and photograph the far side of the moon. Luna 3 would also make another milestone by using the system to be the first spacecraft to be 3-axis stabilized in space, albeit even if it was for a short period. Both Luna 1 and 2 had 4 whip-like antennas protruding from the back half of its sphere, and were used for sending back the measurements from its various science instruments. It would use 3 separate radio transmitters to broadcast on the frequencies of 183.6, 19.993, and 39.986 MHz. I do not know how much power these transmitters used, but it probably wasn't a whole lot. I also do not know if Luna 1 and 2 used different channels, or only broadcasted 3 readings at a time at these frequencies. But if anybody has more info on the transmitters, feel free to let me know in the comments below. Luna 3 would also see these 4 antennas as well, but being flipped to its top half, and with 2 added below. The reason for this is that Luna 3, to minimize movement, had to orientate itself flying topside first. This meant that it could not flip itself around, and therefore needed communications both above and below the craft, since it would be facing to Earth when coming back. This would also be the reasoning behind the 4 front, 2 back placement for Luna 3. Its frame would consist of 2 transmitters using the 183.6 and 39.986 MHz frequencies, with the 183.6 MHz transmitter being the transmitter that transmitted the lunar photo signals. As with the other craft, I have no idea on the output or channel usage info on Luna 3's radio transmitters. However, I do know that they had to get within 25,000 miles of Earth to receive a clear enough signal to be gained. Alrighty, that about wraps things up for all the basic systems on the earliest Luna craft. But next up, we will get into the wildest parts of early Luna, the weird looking soccer ball thingy, and the USSR imaging system. Okay, first up, because it shall be brief, is the Soviet moon pendants, or the soccer balls as I lovingly refer to them. The soccer balls, footballs, whatever you want to call them, were 2 metal spheres with one measuring 3 inches and another one about a little bit larger at 4.7 inches. These spheres were made up of various pieces of titanium Soviet plaques that were also lined with a thermal-resistant enamel coating. The core of this sphere, however, is the most interesting. For nestled inside of this soccer ball is a layer of liquid and an explosive charge. Yes, you heard that correctly. The Soviets and the OKB-1 boys put a straight-up space shrapnel grenade flag in this thing. Now, while the USSR would later go on to sign the 1967 Outer Space Treaty, along with the United States and other nations, making space to any of them unclaimable, this is still the closest thing to a victory space firework I have ever heard of. Okay, enough jabbering on about the rest of Luna. You want to see the camera system, don't you? Well, here it is. And here's a diagram for it. And yes, all of this is being done in space. The USSR imaging system, and that's the last time I'm going to attempt pronouncing that for my sanity's sake. Let's just call it the Y2 for short. Okay, great. Now that we got that covered, the Y2 was the complex hybrid imaging system used by Luna for capturing its photos of the far side of the moon. I use the term capture because Luna 3 could not just simply transmit live images from the moon. Oh no. This would require, and be successfully done, by capturing the far side using real, actual photographic film. This film would need to properly develop and be readable in extreme conditions, and when looking around the country for a suitable film, the camera's design team kept coming up empty-handed. There was, however, one type of film the team knew nothing about. A few years earlier, in 1956, the Soviet government would end up recovering a small number of crashed American Project Genetrix spy balloons. When given access to inspect and looked at the wreckage from these spy balloons, team engineers were amazed at the low temperature and the high altitude properties of the American-made film, as well as its radiation resistance, and knew it was the best option for Luna 3. The camera system's housing would replicate these conditions as best as possible, with the engineers cutting the larger US film to 35mm. They would also go through some length to cut out any markers or numbering, as to not give away the unlikely source of Luna 3's pictures. The film system itself was all mechanically fed, and had a form of temporary storage that was used to store parts of the film for pre- and post-developing. The new unused film was stored in a lead-lined drum, which I can only infer is here on the camera system. Other than this diagram, I cannot find any information on how or where the film travels inside this system, but I would love to know. What we do know, however, is that after being captured, developed, dried, and processed, again, all in space, the film then had to be somehow sent to Earth. And how would you do this in 1959, you may ask? Simple, using a fax machine. Facsimile, or its shorter abbreviation, fax, uses the process of a varied audio, or in this case radio tone, to send information. This works by using said radio tone to plot out spots of darkness, line by line. This process can be used to scan things such as text through a document, much like the businesses did in the 1980s, or to scan a photograph on film, as Luna 3 would do. The transmitting of Luna 3's images was fairly straightforward, but how do you scan this image in the first place? This feature is where the Y2, for its time, would be the most innovative. Its photo multiplier image capturing system. The photo multiplier tube is very similar to the photodetector, in that it collects light, and then converts this light into an electrical signal. The main difference is that, unlike a standard photodetector, a photo multiplier does what the later half of its name implies: multiply the light. This device will be the main physical link between film and electrical data for Luna 3, and would be the key device to achieving its mission. This photomultiplier was then combined with a cathode ray tube. Commonly referred to as a CRT, cathode ray tubes can project electrons, or light, in a narrow beam that can be manipulated back and forth through the means of magnetic fields. This process is called scanning, and this process, at a much higher speed and fidelity, is the basis for how live television was accomplished before cable and flat-screen televisions. This CRT would be placed above the film and the photomultiplier of Luna 3, and would use this controlled beam to scan through its photographed pictures and onto the photomultiplier. Both the CRT and photomultiplier were used in conjunction to get as much detail and clarity of the moon as possible. It should be noted that the photomultiplier on Luna 3 also had no actual image capturing capability, only output pulses of lightness or darkness. Because of this, this process was done in real time, with both the ground station and the spacecraft needing to be in total sync with each other to transmit an image, meaning all of it had to be done in one go. This would be the reason why, initially, weak communications and fading signals would hamper image receiving efforts until Luna 3 was closer to the Earth and had a more stable signal, with its transmitter only outputting about 3 watts. The imaging system for Luna 3 would run at a slow and constant pace, using its oscilloscope-based CRT to scan back and forth, or a line as it's known, every 0.8 of a second. With 1,500 lines per frame, it took Luna around half an hour to send back one picture, with the transmission lowering the resolution to a still respectable 1,000 pixels per line. After sending each picture, Luna would then need 40 minutes to recharge its batteries. This process would be successfully repeated 17 times between October 8th and 18th to get photos back down to Earth from Luna 3. Out of the 40 frames of film on Luna 3, we know at least 5 were test patterns, and that the previously mentioned 17 photos were acquired. 6 of these moon photos were published, and around 10 are known to exist. A man by the name of Don P. Mitchell has done some quite frankly incredible documentation on Luna 3, and if you want to dive deeper into Luna 3, or check out some of the original moon photos, then I highly recommend checking out his webpage on the subject, which I will link in the description below. To sum it all up, the Y2 camera system in all of early Luna was an incredible feat of late 50s engineering. I completely love the fact that its photo capturing method is just a really fancy 1-hour photo in space, or the first Wi-Fi enabled Polaroid. I'm not sure, but nonetheless it's just ridiculous. Learning about this craft has surprised me every step of the way, from the space darkroom to the US spy balloons. It's just absolutely fascinating stuff. Another fact I found interesting is that famed British astronomer Bernard Lovell actually recorded radio transmissions from Luna 2 and 3, and would be instrumental in proving the Soviet feat to the rest of the yet unconvinced Western world, even being reported to play Luna 2's signal live by telephone to New York news reporters. Such was his conviction of the event's occurrence. Well, that about wraps it up for this video. Subscribe to my channel if you'd like to see more in-depth reviews on other unique and forgotten spacecraft. I'm Ben, this is Retro Rockets, and I hope you have an amazing day.